Hey guys, for those of you who might want a little bit more support rather than going through the Google slide presentation by yourself, if you feel like you'd like some explanation of some of the information that's on the slides, we've put together this video for you. And before I get started, because this is the very beginning of our unit on physics, I do want to let you know that we actually have a theme for the entire year, and our theme is forces in eighth grade science. So we will be talking about forces in physical science. We'll be talking about forces when we get to earth science, and we will still be talking about forces when we get to life science. And you'll see us over and over come back to that theme of forces all year long. So we're going to start with what we call motion basics. And so we already gave you a phenomenon, and we asked the question, how do you know when something's moving? So let's move through this Google slide presentation. Remember that when you get to a slide that has a picture of a pencil, there will be some highlighted words on that slide. And those are the words, that's the information we would like you to include in your science notebook. And so what you would do for this is just pause this video while you get your notes written down, okay? All right, so here we go. Oh, let's see. All right. So here's a part of our answer. Whether an object is moving or not actually depends on what we use for comparison. So on the left, here's a picture of a young student sitting at his desk. He might be fidgeting, but really, if we compare him to his desk, we would actually say he's not really moving away from the desk. The distance between the boy and the desk is not changing. But what if we change our perspective? Instead, what if somehow I could get in a spaceship and go and hover above the Earth and look down as the Earth is rotating, and X marks the spot right here. Here is still our young student sitting at his desk, not moving from his desk. But if I compare the motion to something different, if I'm hovering up here and I'm watching as the entire Earth rotates, then I would say that the boy is in motion. In fact, at the equator, he would be moving at about 1,000 miles per hour as the Earth rotates on its axis. So whether or not an object is moving actually depends on what we're using for comparison. Here's another demonstration of how this looks. So let's watch very quickly, and I'll show you this. Hopefully this will record okay for you, but you can also click it yourself as well. So let's pretend that we are at a train station, and you can see that there is a man standing here. I'm going to start this in just a minute, and I want you to pretend that you are standing right behind this person at the train station. You're standing right behind this person at the train station. Now, if we are standing right behind this person, then I would tell you that this person right here is not moving. The train is moving. The train and the people on the train just moved right past us. But I'm standing here. This person is standing in front of me. The distance between me and this person is not changing. So I would say this person is not moving. I would say the young lady that just went by on the train in front of me is moving because the distance between me and that young lady changed. So from this perspective, this person's not moving because the distance between me and that person didn't change. But the train and the people on the train are moving. Well, what if we change our perspective? Now I'm going to pretend that we are on the train, and in fact, we're sitting right beside that young lady. So let's change our perspective. Now, if I'm sitting right beside this young lady, look what happens. See our guy? Now, in relation to me, this young lady is not moving because I'm sitting right beside her. I'm not moving away from her. The distance between me and this young lady is not changing. So now, from the point of view of a person riding the train right here sitting beside her, she's not moving. But now that the distance between me and the guy on the platform did change. And so now I would say the train station and the person standing on the platform are in motion. So whether something is moving does depend on what we are using as our reference point, as what we are using to compare things to. So this is what you would want to write down. We can describe the motion of an object by its position. And we use something called a reference point in order to figure out if something is moving. A reference point is a place or object used for comparison to determine if something is in motion. So how do we know something is moving? An object is in motion if it changes position over time compared to a reference point. And so that does mean that an object can be in motion compared to a certain reference point, but compared to a different reference point, it might not be moving. So scientists really like to describe the motion of objects in lots of different ways. And these are some of the things that we will be using and talking about in this unit. We will learn to understand how we calculate speed. We're going to understand the difference in speed and velocity and acceleration. We will understand which things require vectors in order to describe them. We will be using some math formulas as models to describe motion, and lots of graphs and charts. So these are just some of the things. And actually, when we get to the graphs, we have several different types of motion graphs that we're responsible for. So we want to make sure that you're comfortable with all of these. So to describe motion, a real common thing that we like to do is to describe how fast something's moving, or I guess how slowly something is moving. So the faster something's moving, the less time it takes to travel a certain distance. So you guys know that. So if you run a certain distance, you're going to get somewhere faster than if you walk that same distance. So you're ready to write down our first kind of official definition. So one of the ways we like to describe motion is by talking about the speed of an object. So it's just the distance traveled divided by the time taken to travel that distance. And here's an equation. Speed is equal to distance divided by time. And this always gets me kind of tickled. We take for granted when we're in a car and we're going somewhere and we see that the speed limit is 70 miles per hour. We don't think much about that. 70 mph, no big deal. Well, think about that, guys. That is speed. And then it's just saying speed, mph is miles per hour. So speed is miles. That's a distance. We say per, P-E-R, when we are putting our little dividing line here. It's ratio per hour. So miles per hour. An hour is time. So you're already using speed all the time in your everyday life. You probably just don't think very much about it. So here's some examples of some combinations that you might see. Remember, the key is that all of these have a distance on the top and a time on the bottom. So here's our miles per hour. We're pretty comfortable with that. We see that all the time. But maybe I'm talking about, I don't know, a little worm or something. And maybe I want to describe how far the worm travels in a day. And so maybe the speed of the worm would be best in centimeters because that's still a distance divided by day, which is time. Or maybe I want to talk about feet per second, how many feet per second something is traveling. Feet is a distance and second is a time. So we always have a distance divided by a time. The speed of an object usually doesn't stay exactly the same. Now, if it does stay exactly the same, we would describe it as being constant. But to make things kind of easy for us, we are really going to be working mainly with what we call average speed. So instead of just describing the speed of an object at an exact moment of time, which we can do, that's called instantaneous speed, but we're going to focus more on what we call average speed. And that just describes the speed over a stretch of time. And I'll show you what that looks like in just a second. So to be real careful with our equation here, you notice that we added some words, and we would say average speed is equal to the total distance that is traveled over a total amount of time. So, for example, if I get in the car, I live in Kingsport, and I go over to Johnson City, I want to go over there and go shopping. Um, I'm not going to go the exact same speed the whole time. I'm not. I'm going to go through my neighborhood, and I'll be going very slowly as I travel through, and then I've got some stop signs. And then I'll be getting onto the interstate to travel over to Johnson City. And I might get to travel at a pretty constant speed for a while, but then maybe I get behind some traffic and I have to slow down. Or maybe someone is trying to merge in front of me. So I'll be slowing down and speeding up as I go, and then I'll make my way to Johnson City, and I've got to take the exit ramp, and so I'll be slowing down again. Now, I could calculate at any instant exactly what my speed is at that instant, that moment in time, but that's not really what I'm interested in. I'm way more interested in, you know, how long did it take me to drive to Johnson City? And what was my average speed? So if someone said, what was your average speed when you got to go over there? I say, oh well, it Johnson City is 20 miles away. I don't know how far. I'm gonna say 20, and and it's 20 miles away, and I don't know. It took me, I don't know, it took me about 20 minutes to drive because I'm on over here on this side of, I'm on a side of Kingsport that's closer to Johnson City. So it took me, about 20 minutes to get over there. So my total distance is 20 miles divided by my total time. And if I do my time in minutes, that's 20 minutes, and 20 divided by 20 is 1. So that tells me that I was going about 1 mile every minute. Fine by me, 1 mile every minute. That's okay. And if I convert that into an hour, okay, so I know that there are 60 minutes in an hour, that tells me I was going about 60 miles per hour. That was my average. I wasn't going that fast all the time, but that was my average speed. So here's an example of something that you might see on a quiz, and you'll get some practice with this. So we're not going to ask you to write this down because we already know we're going to be doing some practice problems like this, but here's some cute little penguins. And it turns out that most penguins walk around 2 miles per hour. 2 miles per hour. But they can swim much faster. So if a penguin swimming underwater goes 20 miles in 2.5 hours, what is its average speed? So here's our distance. Here's our total time. So it would look like this. Average speed would equal 20 miles divided by 2.5 hours. And if you put 20 divided by 2.5 in your lovely calculator, you will come up with 8 miles per hour. So they can certainly swim much faster than they can walk. They can swim at 8 miles per hour, and they waddle at 2 miles per hour. Anyone know who this is? This is Usain Bolt. I don't know. He used to be called the fastest man alive. I don't know if anyone has already broken his record or not. Usain Bolt set a world record by running 100 meters in 9.58 seconds. So what would be his average speed? Here's our distance. Here's our time. So we would set this up. 100 meters divided by 9.58 seconds is 10.4 meters per second. And I know that we're more comfortable with a different unit. So that is roughly, now this is his average speed, around 23 miles per hour. That's his average speed. Okay, he obviously has to get out of his starting block and get going. So, but this is his average speed. But what if we switch it up on you? What if we said this problem? Sound travels at a speed of 330 meters per second. So you notice we're giving you the speed. We're not asking you to calculate the speed. We're giving you the speed. But now we're asking something different. How long does it take for the sound of thunder to travel 985 meters? Well, I notice that I have speed. I'm given that. And I notice that I have a distance, 985 meters. But now I have a question. How long? How long does it take? So I'm solving for something different this time. I'm actually solving for time. Now here is a nifty little thing that some of you may have seen before. This is a little triangle that you can use to help you know what to do, what math calculation to make when you're doing this. Now, again, for those of you who've already done algebra, you can just simply rearrange speed equals distance over time. You can simply rearrange that algebraically and solve, and that's fine. But for those of us who aren't quite there yet, we can use this. So you'll always be given two of the three of these things. There's D for distance, S for speed, and T for time. If you are asked to find speed, you kind of just cross out the S and you would take the distance divided by time. If you are asked to solve for time, I kind of tell kids you would cover up the T and you would take the distance number you're given and divide it by speed, and that will let you solve for time. Or if you're asked to solve for distance, I will kind of add something here. If you are asked to solve for distance, then pretend that's not there, and you take your speed number and you multiply it by your time number. So you can kind of use this little equation triangle, and whichever two things you're given, it will help you figure out what to do with them in order to solve for the third thing. So let's look up here. I've got speed, so I have speed, and I have a distance, 985 meters. See? So I have a distance and I have a speed, and I'm solving for time. So I automatically know I'm going to need to take that 985, because that's my distance, and I'll put it in my calculator, and I'll divide it by that 330 meters per second. And I will solve that. And I'm solving for time. Now, again, if you set this up, those of you who are comfortable with the algebra, if you set that up, you're going to see that your meters cancel out, as they should, and you're left with seconds for time. And that's what you should end up with. If you're not quite comfortable with the algebra, we're just going to use common sense. If I'm solving for time, then I'm going to look at all of this mess that I have over here, these units, but I'm solving for time. Well, seconds is the unit for time, and that will tell me that that's what I need to end up with. So let me go back to the mouse and I'll show you how this looks. So we set the formula up for you. Speed is equal to distance divided by the time. Remember, I would just cover up, whichever thing you're solving for. So I filled in 330 meters per second. because that was the speed, is equal to the distance. I knew the distance, 985, and now I had to solve for time. So I can rearrange my formula. So again, if you're comfortable with the algebra, you can simply rearrange your formula, or you can use my little equation triangle up there, and we end up with time is equal to distance divided by speed. And so here I am. I set it up the exact same way I said right here. And if you put that in your calculator, it comes up to 2.98 seconds. Now again, algebra students, geometry students, you should be able to just cancel out. You should be able to do that without any issue. Again, if you're not comfortable with the math, it's okay. Just go ahead and use this lovely little equation triangle and then a little bit of good old common sense. If we are solving for time, then the unit that we would use of the available units we have is just seconds. So here's another one. If a cheetah can maintain a constant speed, I'm given speed, of 25 meters per second, it will cover 25 meters every second. Well, that makes sense. At this speed, how far will it travel in 60 seconds? All right, so I'm going to grab my little pen over here again. All right, let's see. I'm given a speed. There it is, 25 meters per second, so I have a speed. How far will it travel in 60 seconds? So I have speed and I have time, and I'm being asked to solve for how far will it travel? Well, that's distance. I'm being asked to solve for distance. So if I'm asked to solve for distance, okay, I'm just going to pretend that's not there. I'm going to take the speed and I'm going to multiply it by the time. I'm going to take the speed and I'm going to multiply it by the time. All right, so let's see if that's what I did. Distance equals speed times time. Okay, speed multiplied by time. The speed is 25 meters or meters per second times 60 seconds. And again, I'm solving for distance, guys. I'm solving for distance. So of my available units that I have in this problem, I have meters and I have seconds. Well, which one of those is a distance? Seconds is not a distance, that's time. But meters is a distance. So I'll use my common sense and come up with 1,500 meters. Again, algebra students, you should be able to just cancel out the seconds and know that you are left with meters, okay? So far we've just said, how do we know an object's in motion? We know it's in motion if its position changes in comparison to a reference point. So whether an object is moving or not depends on that reference point. We said one way that we can describe motion is by using the word speed, talking about its speed. And we said that we're going to focus on average speed, which is just the average distance that an object moves over divided by the average time that it takes, or the total time that it takes to move that. So the total distance divided by the total time. Well, we also have to get into looking at some distance time graphs. And the big trick to understand these, we think, is to always look for patterns. Remember, patterns is one of our cross-cutting concepts. So if we look at patterns and we really think in terms of patterns, it can help us figure these out. So here's an example of a distance time graph that you might be given and asked to do some work with. So this is Journey to the Bus Stop. Every morning, Tom walks along a straight road from his home to a bus stop, a distance of 160 meters. And the graph shows his journey on one particular day. All right, so I notice that the x-axis has time in seconds on the x-axis. I notice the y-axis is distance from home. The very first thing I want to point out to you guys, because kids get this wrong all the time, They look at this line and they think, and this is wrong, that this means that the object or the person is walking up a hill. That is wrong. That is not what this means. This is simply showing you that this object, or in this case it's Tom, has started right here at his house, and he is walking away from his house. When he gets to point B, I notice that the line comes back toward where he started. This does not mean he's walking downhill. That is not what that means. This means that he is moving back towards closer to where he started. And now he is moving away again. And then something interesting happens. The line kind of flatlines right there. That's interesting to me. That means at 100 seconds after he left his house, he was 160 meters away. 10 seconds later, he's still 160 meters away. And 120 seconds later, he's still 160 meters away. Well, that means something interesting to me. It means his distance, his position is not changing, even though the time is continuing. He must not be moving. So let's check this out. Here's some patterns. And what we'd like you to do is, not only do we want you to write these words, we want you to draw these graphs in, and this will help us. And then we'll go back and look again at that motion graph and put some pieces together. On a distance time graph, if an object is not moving, a horizontal line is shown. That simply means that as time is continuing on, the position of the object or the person isn't changing. So they're not moving. Like a flat line, they're not moving. On a distance time graph, if you see a nice line, nice solid line like this, and it's either sloped up or sloped down, that tells you that the object or the person is in motion and they're moving at a constant speed. The word constant means the same. So whatever that particular speed is, it's not changing. They're not speeding up, they're not slowing down. On a distance time graph, that nice straight line, okay, straight sloped line up or a nice straight slope line down just refers, that means they have a constant speed. Their speed is not changing. We can compare the speed of two different objects. The steeper the line, the faster the object is going. The steeper the line, the faster the object is going. So if I was given this graph, first I need to note this is a distance time graph because we will be looking at other motion graphs. And I can see that this dashed line is much steeper than this solid line. So that tells me that object A is going faster than object B. Object A is going faster than object B. And in fact, that makes sense to me. I'll just look at this, okay? I can see whatever distance this is. We can make up any distance we want. I'll say that represents 100 miles. I can see that whatever object A is, it got there at this time. I'll pretend that's 10 seconds. But object B didn't get that same distance until later. So that makes sense to me. Object A is going faster than object B. On a distance time graph, if you begin to see a sloped line, it's sloping up, that is an indication that this object is speeding up. Okay, it started out and now it's getting faster. If you see a line like this, a curved line like this indicates that this object is slowing down. And that should make sense because look what's happening. Do you see how this is beginning to approach and become a flat line? Well, remember we said a flat line means the object, I could extend that on out. Remember that object is slowing down and maybe it's going to stop. Okay, so that will help you make sense. So let's look at this graph again. All right, so now it should make sense to you. Right here, from point A to point B, this is Tom. Tom is walking at a constant speed away from his house. From point B to C, he is walking at a constant speed, but he is coming back toward his house. From this point, I think I'll go back one. I'll keep going here. From this point to this point, he again is walking at a constant speed, and he is walking away from his house. And now right here, he's not moving. The line is horizontal, so he's not moving. The slope of the line, the slope of this line tells you the speed. It's the change in y over the change in x. So it is actually telling you the speed of the object at that point on the line. And since it's constant, we can calculate that. So here, for example, 0 to, let's see what that is, 100 meters, right there, 100 meters. He walked 100 meters. That is his total distance from this point to this point, 100 meters. And how long did it take to go from here to here? Took 50 seconds. And 100 divided by 50 is 2. And that's how I got the 2 meters per second. So I can actually look at this constant rate of 2 meters per second there, constant rate back toward the house at 3 meters per second. Oops, sorry. Uh-oh, too bad. Sorry. There we go. And so this makes sense to me from here to here, walking back away at a constant speed of 4 meters per second. And when I look at this, this looks steeper than this. The slope is steeper. And so that makes sense to me that this is faster, 4 meters per second versus 2 meters per second. And finally, he's standing still and not moving. I don't know. It says he's going to a bus stop, so maybe he's standing there waiting for the bus stop. All right, now, what if I don't really, I don't know. I don't care about all this stuff. All I want to know is what's your average speed for the whole trip? All right, Tom, nice that you walked from your house to the bus stop, and I don't know what's going on there, but I don't care. I just want to know your average speed for the whole thing. Well, the average speed for the whole trip is the total distance divided by the total amount of time. Well, it tells me right here that the total distance is 160 meters. I can also see right here that he went from 0 to 160 meters. So that's the total distance for the whole trip. And how long did it take him to do that whole trip? Well, right here, guys, he actually apparently got there in 100 seconds. It looks like he got there at 100 seconds and then just stood there waiting for the bus. So 100 seconds. So we said that his average speed for the whole trip is 160 meters divided by 100 seconds, and that would be 1.6 meters per second. If I'm solving for speed, I have to have a distance per a line per time. So in your notes, what we'd like you to do is summarize them. And if you need sentence starters, here's some sentence starters are for you. You don't have to use these, but now we would expect you to look at your doodle notes, and we would expect you to go back and write at least a 1-paragraph summary. So speed is, and then finish that sentence. The math model for speed, write that. On a motion map, speed is shown as distance on the y-axis and time on the x-axis. And there's several patterns that we just went over. Well, what are some of those patterns? And what do they mean? All right. Okay, so if you needed support, hopefully that helped you out. And remember, you can go back and pause and make sure that you have your notes.